Good evening, class. Yeah. So today I'll be solving the problem number 3, problem set 3, which will be having 10 number of questions based on the week 2 assignment, and these questions will help you solve the assignment number 2 and also better understand the physics of the week 2 lectures. So I'll start with the first problem. The first problem asks that the number of the conduction electrons per unit volume for silver is 5.86 into 10 power 28 per meter cube. Then the corresponding Fermi energy and the Fermi temperatures are. The question is asking what the Fermi energy and what the Fermi temperature for a given carrier density of 5.86 into 10 power 28 per meter cube. So let's solve it. We know that the carrier density in the given question is 5.86 into 10 power 28 per meter cube, and the question asks for the Fermi energy. The Fermi energy F will be given as, we all know that H bar square Kf square by 2 mass of electron, because these are the free electrons, so we'll take the mass of the electron as Me, and we know from classroom notes, and we can derive it also easy, but I'm just referring to the class notes that Kf is nothing but 3 pi square n to the power 1 by 3. And this you can derive it from the density of from the number of states, available states, and then in the 3D. So the Fermi energy will turn out to be h bar square 3 pi square n to the power 2 by 3 by 2 mass of electron. Now h bar we all know is 1.054 into 10 power minus 34 joule second. N is given in the question, that is 5.86 into 10 power 28 per meter cube. Mass of electron we all know 9.1 in 109 into 10 power minus 31 kg, and pi we all know is 22 by 7. So all the quantities are known, so let's just calculate EF. So EF will be 1.054 10 power minus 34 to square times 3 pi square is, I will take 3.14 square times carrier density is 5.86 into 10 power 28. The power 2 by 3 pi divided by 2 times mass of electron, that is 9.109 into 10 power minus 31 kg. That is. So now I will use a calculator. So the calculation goes like 1.054 into 10 power 10 to the power minus 34 and square of it times P into 3.14 into 3.14 into 5.86 into 10 raised to power 28 and the whole power is 2 by 3. So this gives me 1.602 into 10 power minus 48 divided by 2 into 9.109 into 10 power minus 31. Remember, this energy is in the joule. So let's convert. So let's solve it furthermore. Divide by 2, divide by 9.109. This gives me 8.798 10 power minus 50 minus 31. So t minus 31 is nothing but 19 minus 19 joule. But the given options are in EV. So let's just convert. So EF will be 8.798 divided by 1.6 and multiply by also 1.6 E minus 19. And this is also in the joule, but we all know that this part contributes to the E electronic charge. So the answer which remains is 8.798 divided by 1.6 is 5.498 into 10 power. This 1919 cancels and this turns into EV, roughly 5.5 EV. Let's see. So the option A has the 5.5 EV. Now the second part of the question asks us that what is the Fermi temperature? So the Fermi temperature, how we calculate the Fermi temperature? Fermi temperature. So for calculating the Fermi temperature, EF will be is equals to Kb times Tf. Tf is the Fermi temperature. This implies Fermi temperature Tf is equals to EF. That is EF is nothing but 8.798 into 10 power minus 19 divided by Kb is nothing but the Boltzmann constant, which is 1.38 into 10 power minus 23. This is in joule and this is joule per Kelvin. If I do a bit of a math, then let me just use a calculator. 8.798 divided by 1.38. This gives me 6.37 into 10 power 4 Kelvin. So let's look at the options. So the 6.37, I can roughly write it as 6.4 because it's 10 into 10 power 4 Kelvin. In the options, there is slight corrections. These one are in the units of 10 power. These are like multiplied by 10 power 4. We all know that the Fermi temperatures are very high. It's like 10,000 Kelvin. So the correct option is A, which has 5.5 eV as the Fermi energy and 6.4 into 10 power 4 as the Fermi temperature, Kelvin. So this is how we calculate it. Now, if you have any question or doubt the class, they can ask in the chat box. If not, then I'll be moving on to the next question. which is that if the temperature T for silver is given, it's 800 Kelvin, then find the energy at which the probability that a conduction electron state will be occupied is 90%. Okay, so uh, now we'll have to look at the occupation number in the Fermi-Dirac distribution, that how the occupation number function behaves as a function of the temperature, and that's what they are asking. This question is asking basically. So we know that the occupation number, that is the probability of the occupation basically. So the probability that a conduction electron state at energy E is occupied by the Fermi-Dirac distribution we all know is given as this the function Fe is 1 upon 1 plus e to the power E minus Ef, that is the Fermi energy, by kT. This is kBT. So here E is the energy of the electron, the carrier. Ef is the Fermi energy. And Kb is Boltzmann constant. T is the temperature. And we all know that this function has a shape. This function Fe has a shape so if I plot this function at t equals to 0, so on the y-axis I will plot the function Fe, which is this is my 0 and this is my 1, that is the state is occupied. This is my Fermi energy Ef, I'm calling. So at t equal to 0, the occupation will be like this. This is at t is equals to 0. And at finite t, it will be more or less like this function, which is half here. So the Fermi function occupation number is half at the Fermi energy. And now the question is asking is, what the question is asking is that the temperature is 800 Kelvin, that is a finite temperature, T naught equals to 0. In this regime we are the blue curve. Then find the energy at which the probability that a conduction electron state will be occupied is 90%. So what the question is saying is, what is the probability that this is 90%? Here the value will be 0.9 somewhere, right? 0.9. This is 0.9. The question is asking, what is the energy at which this curve is having the value 0.9? That's essentially what the question is asking. So let's just solve it. Now it's just a mathematics. We know that Fe they are saying to be 0.9. Fe is 0.9, which is equals to 1 upon 1 plus e to the power E minus Ef by kBt. Now, let's just calculate. Just do a little bit of math. That it will be 0.9 plus 0.9 times e to the power e minus ef by kBt is equals to 1. So it will be 0.9 times e to the power e minus ef by kBt is equals to 0.1. And if I do the little bit of math, it will turn out to be e to the power e minus ef by kBt is equals to 1 over 9. And taking log on both sides, taking ln on both sides, ln, if I take the ln of e, it will be e minus ef by kBt equals to ln of 1 by 9. Since this is for silver, and for silver we have already calculated the EF, that is the 5.5 EV. So I'll use the previous calculated values, and kBt is 800 Kelvin. That's given in the question. So I'll just substitute the values. Let me check what the options are, whether in EV or like the options are in EV. So I will adhere it to the EV values. 5.5 by kBt. kBt is, let me just calculate kBt. So kBt will be 1.38 into temperature is 800 and divide by 1.6. So it's 690 into 10 power minus 4. Yeah, equals to ln 1 by 9. Let's just some bit of math. ln 1 by 9 is nothing but minus 2.197. Let me multiply it by 690. Yeah, and then 10 to the power minus 4. So this value turns out to be E equals to EF plus EF minus 0.151 EV, and EF is 5.5. So 5.5 minus 0.151 EV, that gives me E is equals to 5.348 EV. So this is the energy at which the occupation number will be 90%. Let's look. So the correct option is 5.4 EV. 5.335 is the value which is coming, and the only closest value is 5.4. Right answer is 5.4. Yeah. Now let's move to the next problem. The next problem is, consider an electron in a volume V with energy given as E is 2 times h bar square k square by 2m, and the band is filled, states are filled up to the level kf. That's the Fermi wave vector. The energy per electron epsilon and the pressure exerted is given by. So this is something which is already being solved in the class by professor, but I will still solve it because it's there in the assignment. So let's just begin it. The energy is given. So let's first estimate the kf for us. So what the kf? So total number of allowed states, total number of allowed states in 3D. We know that n will be nothing but integration over dk d3k d3l by 2 pi cube. So n is equals to d3l will be the volume, and d3k I can write that 4 pi k square dk, 0 to states which are filled up to kf by 2 pi cube. Since the system will be spin degenerate, so I'll have to multiply it with the degeneracy also. So now this will be nothing but 2v 2 cancels, and there will be 1v by pi square k cube by 3, kf cube by 3. And if I do a little math, n by v, so if I just do kf will be nothing but 3 pi square n by v to the power 1 by 3. That's what in the very first question which we used is, this is the relation which we used here in the very first problem. Kf is 3 pi square n to the power 1 by 3. It's the same one. You can see how where the relation comes from. Now the question is asking what is the average energy. So the energy per electron, the energy per electron, the question is asking. So basically E is some 2 times the energy per electron will be E by N, right? That's what the energy per electron is. E is the total energy and N is the total number of the particles, which are the total number of allowed states. And this is K to Kf h bar square k square by 2m. So let's just calculate it. So E by N. Let us divide it by also. Divide this one also by N. So let's just first calculate the E. What is the E? So E will be 2 times, if the integration is there, I will have to take the like dk basically. So dk, the number of the states, I can do the integration kind of thing, and that will give me the full number of the total number of energy, the total energy basically. So I can convert this summation into the integral by using this idea that I can divide it into the small sections, and we'll come to the point where one section will occupy only one allowed state basically, and from there I will integrate to the filled states to the kf, and that will give me the, so d by 2 pi cube times d3k. This is the occupied by the one state. This is the volume occupied by the one state. So let's just do the integral. 2 times 0 to k. Okay, let's take out the constant first outside. So 2 h bar square k square by m pi to the power cube 0 to kf. K square I cannot take out, so k square will remain inside. D3k, the v I can take out. D3k I will write at 4 pi k square dk, and E will be h bar square b m 2 pi cube 4 pi k to the power 5 of 4 5 to the kf. This is h bar square b times 4 pi is nothing. This, let's just do the calculation here. So it will be m times 2 pi square times kf to the power 5 upon 5. So let's distribute it. I can write it like v by 5 pi square times h bar square kf square by twice m times v by 5 pi square h bar square k square by 2m twice m multiplied by kf cube. That's how I can write it, right? And if I write it, v by 5 pi square h bar k square by 2m is nothing but the ef times kf cube. So let's move on to this equation. 1, 2, substitute 1 into, substitute 1 into E will be V by 5 pi squared EF times KF cube is nothing but N times pi square divided by V, N times pi square divided by V and multiply by 3. So this goes as EF times V cancels, pi square cancels, EF times N times 3 by 5, and the question is asking is the energy per unit state, that will be the average energy divided by total number of particles, that will be 3 by 5 times EF. Let's see, is there any option 3 by times time EF? Okay, right? And EF I can write, since the question is asking in kbtf, I can write it as like kb times tf. So 3 by 5 kb times tf. So at least this answer is correct, the B. Now let's look at the pressure exerted at the degeneracy pressure. So let's just calculate the degeneracy pressure. Somehow the page is not getting added. Just close the notes and open it again. Yeah. Now the exerted pressure. We all know that from the thermodynamics relation that the pressure will be minus del E by del V at a constant number, constant carrier densities basically. And since we all know that is E by N, average energy by N, and that is like this implies this energy is V by 5 that we calculated, N times EF, we already have it, and N is nothing but this is the carrier density. 1, 2, so let's just do some maths here. P is del E by P by 5 NEF del by del V. And let me write the EF also in terms of the EF also I can write in terms of N. So EF is nothing but h bar square k square by 2m. And kf is 3 pi square n to the power 1 by 3. This gives EF as h bar square 3 pi square n to the power 1 by 3 by 2m power 2 by 3. Let's just this is not needed, and let's just substitute these things in substitute 2 in 1. This implies E as 3 by 5 times n times EF is h bar square 3 pi square n to the power 2 by 3 by 2m. So let's just take the derivative of it. Del E by del V 3 by 5 times n times h bar square times 3 pi square n to the power 2 by 3, and n to the power 2 by 3 goes as 2 by 3 square to the power 2 by 3 and 2 by 3 n minus 1 by 3 by 2m. Three cancels, so it equals 2 by 5 times n times actually it will be 3 pi square n and v to the power minus 2 by 3. So minus 2 by 3 and v to the power minus 5 by 3, which I can write as t to the power 2 pi n to the 3 to the power minus 5 by 3. And if you just transfer the v inside and do the calculation, let me do it. So minus del e by del v. So this is 2 by 5 n times h bar square p pi square n by v to the power 2 by 3. I can take it in times v to the power minus 1, which I can take it here, and by 2m. And if just I do it, it is nothing but 2 by 5 is 2 by 5, n by v is n, and this term, you see, recall it, it is EF. So the degeneracy pressure will be given as 2 by 5 times n times EF. Let's just see whether this is the option. Degeneracy pressure should be 2 by 5 times n times Vf, but here they are asking it in terms of E by V, basically this energy, total energy. So this total energy also we can write in this form also we can write. So let's just recall this relation. They are asking us in this form. So let me just just copy it. Just in which form they ask the question, we will just transform it to that form. Paste. It is nothing but 2 by 5 n by v times EF. Let's just substitute the EF here. So if I substitute 2 by 5 times n by v times EF, instead of EF 5 by 3 1 by n times E. So that will give me 5 cancels, 2 by 3 E by V. Let's just see whether this is the option. 2 by 3 E by V. So this is the option. That's the solution for question number 3. If any question or doubt, you can ask me. If not, we can go ahead. The Fermi energy of a metal is 5.51 eV. So if this is the Fermi energy, this is for silver actually. We have calculated, right? So we know Fermi energy EF is 5.51 eV. The average energy of the electron at 0 Kelvin is given by average energy of the electron. So that is nothing but E by N. Basically, this term, this is. Let me just write it better. Let's write it E by N. That's what they are asking. This E. The temperature at which the classical field particle is given by T and the ENTR. Okay. First, they are asking this term. E is E by N. We know that from this relation, this will be EF times 3 by 5, 3 by times of EF. So 3 by 5 times of 5.51, 5.51 times 3 divided by 5, that will give me 3.306 EV. That directly tells me that the answer number is A, but we have to compute the temperature also. And to compute the temperature, classically, since they are saying classical free particle, for classical free particle, energy is equals to 3 by 2 times kBT. This implies 3 by 2 kBT is equals to this energy, average energy per electron. That is 3.306 eV. Let's just transform it. T will be 2 by 3 times 3.306. It's in electron volt. Let's convert it into the joule. And then kBT is nothing but 1.38 into 10 power minus 23. So this will be 2 times 3.306 times 1.6 divided by 3 divided by 1.38. This is 2.55 into 10 to the power 4 Kelvin. That is nothing but the answer number 1, 2.55 into 10 power 4 Kelvin, and the energy is 3.3 eV. So this Fermi temperature is so high that tells us that this is the temperature which is required. If so, you know that the Fermi C. So the electrons are filled from the lowest energy level to the energy EF. So this is the temperature which is required if you want to kick out this electron on the surface. If you want to bring this electron on the surface, this much energy is required. So the 2.5 into 10 power 4 Kelvin. At this temperature, the metal itself will melt. So whatever the metal you can think of, the silver, gold, they will melt at this temperature. This is very large temperature. So the metal will lose its property before you can kick out the electron which is last there filled. So that's what it means, the Fermi temperature, the physical significance of this much high Fermi temperature. And this comes from the Pauli exclusion principle, because you cannot fill the two states in a single, two electrons in a single state. The Pauli exclusion principle don't allow it to do. and that's why there are states which are filled on top of each other, kind of thing, in the increasing energy order. And they come out to be the topmost energy state till which the electrons are filled is roughly 5.5 EVs, for example, in silver. And you will require the temperature which is like extremely large, 2.5 into 10 power 4 Kelvin, to just kick out the last electron which is sitting there in the bottom to bring it out on the top. And this tells you the one more thing which is very important, that not all the electrons in a metal participate in conduction. The electrons which are near the Fermi energy, you can only excite them, the KBT, that much energy range electron you can excite only. So the electron which are there here, EF and the KBT range, these many electrons will play the major role. The electrons which are filled down there, they cannot play anything because they cannot contribute. So the electrons which are near the Fermi energy, they are the one which contributes. This is the another side of this uh, temperature range, that we should only look mostly that the for the transport properties and all those things, the electrons which are filled near the Fermi level, not the well below, not the well above, right at the Fermi level. And that if you are sitting at temperature T, then in the KBT range, they are the electrons which will contribute. Being it the specific heat, being in the connection, all those things will be contributed by those electrons. Now moving on to the next question, that consider two electrons in a box of length L in ground state energy given by epsilon naught. Now two boxes are pushed together to form a bigger box. Which of the following statement is not true? So let's just make the two boxes. This looks like to be, to me, the classic, the signature problem of the quantum mechanics in the particle in a 1D box. Consider two electrons in a box of length L in a ground state given by epsilon naught. Now two boxes are pushed together to form a bigger box. So the question is saying that there are two boxes of length L. So I will take it 0L, and this is also 0L. And there are electrons in it. So there is one electron in a box. And I'm drawing it the lowest energy for the state, the ground state, because the system is asking for the ground state. And let's say the spin is up or down or whatever it is. Like I'm taking up, or I can take it up, down also. Doesn't matter because they are well far up, far away from each other, so they don't interact till the point. So now let's just calculate the ground energy. Calculate the ground state energy. So this is the wave function kind of thing, and we know that this lambda is, so how do we define lambda for a wave? This is the lambda. So here lambda by 2 is L, right? And K, we define the wave vector. For a wave like this is 2 pi by lambda. That tells me that 2 pi by lambda is 2L. That gives me pi by L, K to be. And ground state energy for two non-interacting electron in 1D box, in two 1D boxes, because they are non-interacting, they are far away, will be 2 times n square pi square h pi square by, okay, let me just write it like this, h bar square k square by 2m. That will make more sense. So this is h bar square k square by m, and k is nothing but pi by L. This tells me that energy epsilon naught, whatever the question has given, is E naught, not the epsilon naught, E naught, is h bar square pi square by m L square. This is the ground state energy, as the question has given. Now, let's look what the question says. Okay, somehow it's to share the screen again. I think the screen got share my screen. Yeah. Somehow it's not coming. There's some lag in the software. Got to fix it, but sorry for the somehow the things got erased. I don't know. I will write it again, but somehow the things got erased. The software is not behaving the way it should. But I remember the value, so I will write the value h by square pi square by m L square. This is the epsilon naught. Now two boxes are pushed together to form a bigger box, whether the following is not true. Now two boxes are pushed together to make a one big box. That means now that both the electrons are in single box, but we know that the ground state will be achieved if one is top spin and the other is down spin. And 0 to, now this is 2L instead of L because they are pushed together to form a one bigger box. And if that's the case, then I can replace this L by 2L. So new ground state energy will be h bar square pi square by 4ml square. That will be of epsilon E naught by 4. So the electron will the opposite spin occupy ground state with E is equals to net by 4. This is true. And the question is asking which is not true. The first excited state is given as this. So first excited state will be n square pi square h bar square by 4ml square. N is equals to 2. This gives E naught. This is also true. Let me write them. True, true. The first excited state is given by, this is false. Using Heisenberg uncertainty principle, the momentum decreases by half. So what the Heisenberg says, that delta x, delta px is h bar, roughly h bar. So if my, so in this case, initially it was L times px. L times px was h bar initial. In the second case, it will be 2L times px. So this is, let me call I, px final, h bar. This 2, this tells me that px final is pxi by 2. So this is also true. So the correct answer is this one. That this is not true basically. So that's what the question is asking, which is not, which of the following is not true. So Now, moving on to the next question. If you have any question or doubt, you can ask in the chat box. I'll be answering those questions. Okay. Now the next question is: in a whole experiment in a metal, a potential of 4.5 microvolt is developed across a foil of thickness 0.02 millimeter when a current of 1.5 ampere is passed in a direction perpendicular to a magnetic field of some Tesla, the Hall coefficient for the metal. Okay, we know Hall coefficient. Let's just see what the Hall coefficient is. RH, right? We define it EY by JXD, where EY is transverse electric field, Jx is the current density, and B is the magnetic field, which is perpendicular. Okay, now let's just draw whatever the question is saying. The question is saying there's a plate on which these things are happening. So let me just draw a plate, and then just copy, then paste. Okay, well, fine. Okay, cool. So the thickness which is given is 0.2 mm, 0.02 mm, extremely thick. In a metal, potential which is developed between the transverse potential they are saying, which is developed is 4.5 microvolt between the point A and the point B, the edges. When a current of 1.5 ampere is passed in a direction. Okay, cool, fine. So what will be the EY? EY. EY is nothing but the potential between the A and B divided by the length. Let me call this one as length L or W. This is actually width, not the length. IW. What is my current density? Current density will be I divided by this area basically. This area will be W times thickness T, that is 0.2. W times T, and B is the magnetic field. Let's just see let's just substitute all these values. EY is VAB by W, Jx is I, W times T times B. So this is VAB times thickness divided by I times B. So Hall coefficient RH will be nothing but VAB is 4.5 microvolt. Micro is 10 power minus 6. T is thickness, that is 0.02 into 10 power minus 3 meter. Current is given as 1.5 amperes. And B magnetic field is 2 Tesla. So let's just calculate this RH. I have the calculator, I will use it. So 4.5 times 0.02 divided by 1.5 divided by 2. It will be 0.03 times 10 power minus 9, or 3 into 10 power minus 11, right? So 3 into 10 power minus 11, and if I look at the units, it will be meter cube per coulomb, I think. I'll just check the units. It will be meter cube per coulomb, And the question is asking in terms of 10 power minus 10, not minus 11. So if the question asks minus 10, so I will make it 0.3. So the correct answer for this one will be 0.3. If you have any question or doubt, you can ask me. Otherwise, I will move on to the next question. For the same problem as question number 6, the electron density in the metal is IC. Now they are asking, okay, fine. Now you have calculated the Hall carrier density. Okay, now you have calculated the Hall coefficient RH. Fine, good, well and good. The question is asking, what is the carrier density? Now the question is asking, what is the carrier density? We all know that the carrier density from the class notes you can refer. N will be nothing but 1 by E times the RH. RH is the Hall coefficient which we have calculated. So N is 1 by E is 1.6 into 10 power minus 19. RH is 3 into 10 power minus 11. So 19 and 11 will be 29, and 1 divided by 1.6 divided by 3. So it will be 2.08 into 10 power 28 per meter cube. Yeah. So this will be the Hall carrier density. This will be the electron density or Hall carrier density, whatever you call it, 2.08 into 10 power 28 per meter cube. Yeah. If you have any question, you can ask me in the chat box. Now moving on to the next question. The Hall probe consists of a copper strip where electron density is given, where electron density is 8.5 into 10 power 28 electrons per cubic meter. Okay, which is 2 centimeter wide, 0.1 centimeter thick. What is the magnetic field when I is 50 ampere and the Hall potential is 4 microvolt? Okay, fine. Now we have been given RH. No, we have not been given RH, but we know that RH is EY by JXB, and which is equals to 1 by NE, right? If you substitute the EY's JX values, this has been done in the class. Refer to class notes. You will get it in the class notes. So RH is EY by JX by B, that is equals to 1 by NE. Now what they are asking is what is the magnetic field. So let's just solve this equation. B will be JX by EY and E. So the thing which we have here is something like this. The one which we have shown similar to that same exact. I see one line here, one line there. Let me just copy it. Okay, fine. The question says that it is 2 centimeter wide it is 2 centimeter wide and 0.1 centimeter thick. This is 0.1 centimeter. So this is my T, this is my W. And then we will do the same exercise. So Jx it will be nothing but I by W times T. Ey will be nothing but if there is a potential difference between A and the B point, PAB divided by W. So substituting these in equation 1, this is my 1. So Jx will be I by Wt times Ey is VAB times N times E and times W. Yeah, this W cancels. So B is nothing but I given in the question is 50 amps. 50. T is 0.1 centimeter. 10 power minus 2. BAB is 4 microvolt. It will be 4 into 10 power minus 6 times N. N is 8.5 into 10 power 28. And 1.6 into 10 power minus 19. Let us just calculate these numbers. So it will be, let's just first calculate the powers. 28 minus 19 minus 6. And if I write it at 1, so that will be 3. So everything cancels out on the bottom. On the top, it will be 50 divided by 4 divided by 8.5 divided by 1.6. So that gives me 0.91 Tesla. This will be the magnetic field. This is the magnetic field which will be required to. Or did I do something wrong? Let me just calculate. pH times T times Ne by So this whatever I calculated is inverse of T, but this is 1 by B. This is 1 by B. So this gives me 1 by 0.91. That should be the correct answer. 1.0.91. That is 1.09. This gives B is equals to 1.09 Tesla. This is Tesla inverse. Yeah. So this is the solution of the problem number 8. If you have any doubt or question, you can ask me. If no question, then I will move on to the next problem, which is the following is the dimension of a Lorentz number. Lorentz number. So we all know from Weidmann-French law, Weidmann French law, that Lorentz number is equals to K by sigma T. That's how it's been defined, right? where K is the thermal conductivity. Sigma is the electrical conductivity, and T is the temperature. So let's just see the dimension of each of the K, sigma, and T, and now after that it will become better. So thermal conductivity first. Kappa is equals to, this will be watt per meter Kelvin, and if I write it, it will be, watt is nothing but joule per second, joule meter second Kelvin, and joule I can write as kg meter per second square, so that will be m s cube and k kg meter square. So and if I do it, it will be kg meter per second cube Kelvin. So kg is nothing but like mass, right? So m, meter is length, as second is, I can write t minus 3, and Kelvin is k minus 1. So that is for the kappa. Now sigma, now electrical conductivity. Sigma is nothing but 1 by omega m, ohm times m, and if I write it, it will be ampere square seconds cube by mass and times the length cube. So this will be m inverse L minus 3 a square s second cube. And now Lorentz number, L is equals to k by sigma t. That means that k is m L t minus 3 k minus 1. Sigma is nothing but, the sigma inverse will be m L cube a minus 2 second minus 3, and then there will be Kelvin on the bottom, k minus 1. This will give m square L to the power 4, and this is like nothing but square kg. So if I do it, it will be somewhat, let me just calculate it. Again, there is software problem, it will hang. Just copy it, otherwise it will hang. I will lose it. Copy. I'll close it and open it again. See, I lost it. Whatever I did, I lost it. So now I won't be able to copy it also. So I'll have to do it again. So Lorentz number, I think you can do it, is it will be k by sigma t, and the answer for it, its dimension will be like length square mass square by time second, basically time to the power 3 ampere square, and then Kelvin square. So if you do it like this, it will be m square L square T to the power minus, I think this will be T to the power 4 T to the power 3, but this will be ampere times the time you can do, so that will give you the coulomb basically. I think so. Okay, let me just write it. If I have the values, I'll just write it again and try to copy paste it. If it gets pasted, paste. Ah, it's no, something wrong, something wrong. Undo, undo. Yeah. So we have it as saved. So m square L to the power 4, and then m t to the power minus 6 ampere square Kelvin minus Kelvin minus 2. Okay. Again, we are not able to add the page somehow. This is getting crashed today. I don't know. Again, it's crashing. Crashes and I lose the information. I'll fix it in the next class, but sorry for the whatever. Yeah. So if you solve it, I'll write the final answer. It will be this one: meter square L square T to the power minus 4. This C inverse K to the power minus 1. This one. Somehow it's crashing again and again, and I don't know what to do with it. But if you do it, that's what the solution. Whatever the equation I had written, if you solve it, if you follow the video, then you can get that answer. Now moving on to the next and the final question, which is the Fermi energy for lithium is 4.72 eV. EF is given, that is 4.72 eV. Density of electron is also given, that is 4.6 into 10 power 28 per meter cube. The electron density for a metal with a Fermi energy 2.35. Okay, EF1 and N1 for a metal is given, and EF2 for a metal is given 2.35 eV, and N2 they are asking what is the N2. We know that EF is proportional to N to the power 2 by 3. Okay, I don't know whether you know it or not. Let me just. So this is something which I derived in the class, N to the power 1 by 3. So, and if I take E as h bar square k square by 2m, this will be h bar square by 2m times 3 pi square n to the power 2 by 3, telling me that EF is proportional to the n to the power 2 by 3. So EF1 by EF2 will be n1 to the power 2 by 3 by n2 to the power 2 by 3. If I do it, n2 is equals to EF2 times n1 by EF1 to the power 3 by 2. That's what it will be. So N2 will be nothing but EF2 is what? 2.35. It's given the question. EF1 is 4.72 to the power 3 by 2 times n. N is given is 4.6 into 10 power 28 per meter cube. So N2 will be nothing but, just use a calculator. 2.35 divided by 4.72 raised to the power 1.5. That will be 0.35 times 4.6. That will be 1.61 into 10 power 28 per meter cube. 1.6 into 10 power 28 per meter cube. This is the answer, which is number 4. And that is the answer. If you have any question or doubt, you can ask me in the chat box. I'll answer your queries. Yeah. If okay, I'll go quickly over whatever we have done in the class, and then we can close the class. So the first question was the number of the conduction electron per unit volume, that is the Curie density was given 5.8 in 10 power 28 per meter cube. Then the question asks what the Fermi energy and the Fermi temperature. We know that Fermi energy is h bar square 3 pi square n to the power 2 by 3 by 2m. We substitute the values. This in the joule, we convert into the electron volt, and that turns out to be 5.5 eV. The Fermi temperature we calculate as EF is equals to kBT, and the Fermi temperature is 6.4 into 10 power 4 Kelvin. In the question, it was, the 10 power 4 was missing, so I have written in the question. Now, in the next question, the temperature for silver was given 800 Kelvin, and the probability that a conduction electron state will be occupied is 90%. So that this is Fermi occupation number. Fe will is 1 by 1 plus e to the power e minus ef by kt. That this function tells that what will be the occupation number, the probability of occupation for the electron, fermions basically. And whenever it will be 0.9, we want to calculate that energy. So we substitute 0.9 as Fe, and we take the Fermi energy from the previous question, kBT. Kb is the Boltzmann constant, T is the temperature, which is the 800 Kelvin given in the problem. We solve it, and turns out to be 5.348 eV. And in the next question, which is the same problem which has been solved in the classroom. So, and the same thing which I did in this assignment also, that first we calculated the Kf in terms of the n, then the energy per electron, we convert the summation into the integral, and from there we get the total energy to be 3 by bar times the Fermi energy, and the energy per electron will be 3 by 5 times EF. Then we also calculate, we go on calculating the exerted pressure, that will be total energy derivative with respect to the volume at a constant number density, and from there we do the calculation. The calculation you can follow, and this gives me pressure exerted will be 2 by 3 times EV, E by V basically. Next, in the next question, what is the Fermi energy, what is the average energy basically, that will be the 3 by 5 times the EF. EF is given, we calculate the average energy, and then the temperature. What is the temperature? So temperature, for assuming it to be the classical, so that got erased because of the software crash, but I will just write it again. P by 2 kBT will be is equals to 3.306 into 10 power minus 19 into 1.6, and from here you calculate the T, that will be, I think if I'm not wrong, it will be 2.55 into 10 power 4 Kelvin. Yeah. Then in the next question, there was 2 electrons which were there in the separate boxes. Their energy was given to be epsilon naught. We calculated it, assuming it to be of length L. That's given the question. Then and the E naught turns out to be h bar square pi square by ml square. Now the 2 electron comes together, these 2 boxes, and they merge into a single box. This is the bigger box, length 12. We calculate its occupancy, but the ground state energy, and we find that the electron with opposite spin will occupy the ground state with energy epsilon E naught by 4. The first excited state will be given as E is equals to E naught. It also is true. The first excited state is given by E is equal to 4 E naught. That's false, because of course the ground state, the first excited state will be E is equals to E naught. And using Heisenberg uncertainty principle, we show that the momentum will also decrease by half. So that's also true. In the next question, this is a classical Hall bar problem, Hall effect problem. You apply a like a potential difference between the 2 points. Current starts flowing. You apply a perpendicular magnetic field. There will be a transfer developed voltage, and from there you can calculate the Hall coefficient. And not only the Hall coefficient, from the Hall coefficient you can calculate the whole carrier density, by the carrier density, carrier concentration. This is the measurement which is very vital and crucial in terms of the 2D material, and to determine the carrier density very precisely using the Hall effect. So this is something which is a technique which is used in the experimental condensed matter very often. This gives accurate results. The next one is a Hall probe consists of a copper strip with the electron density is given. This is 20 centimeter wide. The same problem, we solve it and we get the magnetic field which will be required to produce this much voltage is 1.1 Tesla. That is achievable using the superconducting magnets. Nowadays, basically niobium magnets are there, which like at low temperature are superconductor, and one can obtain this much magnetic field easily, and can see these Hall effect and way better than this, like the quantum Hall effect or fractional quantum Hall effect. Then we go on seeing what will be the dimension of the low range number. This also we did here, the software best. You can follow on the video lectures. And in the last question, the Fermi energy was given, the carrier density was given. For another metal, the Fermi energy was given, and the carrier density they were asking. So we can just take the ratio of this equation. Yeah, this equation EF1 by EF2, and that from there I can calculate the N2. That's the whole carrier density. The carrier density. If you have the data for the 2 of the 1, and the 10 carrier density is 1.61 10 power 28 per meter cube. So this is something which we did in this class, and the assignment 2 is complete. And the next class I'll be following up on the third assignment, which will be from the week 3 classes. And if you have any question or doubt, you can ask me in the chat box. I'll be happy to answer your questions. If not, you guys can leave the class.